Right, so I'm gonna go ahead and get started. I hope this is recording. If it's not recording, I'm gonna re-record this later. Um, but I'm gonna go ahead and jump into it. So today I'm going to talk a little bit about some of the content that you need to understand before jumping into the lab. I'm also going to talk about how to get into Pivot and if uh, sorry, I'm checking some things out, making sure everything's in its place. All right, and I'm going to run down a couple of those sort of like how-to using Pivot. So should be a pretty informative session, if not pretty quick. Uh, if you have any questions, you're always welcome to, if you're watching this on the recording, if you have any questions, you're always welcome to reach out to me and ask, or better yet, right now we're looking at the Canvas page. You can go over to the discussion board and you can go to the FAQ and you can ask your question there. So a couple of different options. And you'll also see another discussion board. We'll talk about that towards the end of the Zoom session. All right, so jumping right up front, going to the home page. This is where you're going to land every time you enter the physics, every time you enter the physics page for this class. Sorry, I'm just opening up my email on my phone to make sure I'm going to see any of those that pop in case somebody needs to get a hold of me via email. Okay. So this is where you're always going to start off and, important information right up front, where you can find me, office hours, Zoom hours. My Zoom hours are probably going to change as well as the time I'm holding this class, probably going to change. Keep an eye out in your emails in your inboxes to see a message from me saying, hey, need you to fill out the survey for you to tell me your availability, and then I can schedule probably a better time for us to all meet up. My email, of course, right up here. Several of you have already emailed me, so I know it's up and working. Good at communicating so far. I want to talk about some announcements right up top. So first and foremost, welcome to physics. I wanted to send out a reminder about this class. This is the first email of the week, and it's just saying, hey, we're having a Zoom session. Again, attendance is always optional. This is an asynchronous class, but it's a great time to come in and ask questions as I go throughout the lecture portion. Another announcement that I made was in regard to Pivot access. We'll get into talking about how to access Pivot. And I just want to remind you that if there's a barrier for you to get a license, like let me know. I have several of the licenses I purchased for you guys, for the students that need them. But you gotta let me know ASAP so we can get rolling with this class. Jumping into the modules, we have our week one activity. And our week one activity, when you click on it, it takes you to a place where you're linked to enroll in physics interactivities. That is where our activity is going to take place. If you click on this link, it takes you to a place where it fills out your class key. This is specific to our class, and it'll populate with the class name and the instructor, myself as well. When you press confirm, it takes you to a place. If you can pay the $10, hey, that's great. If you cannot, then please, please, please call me and not call me, email me, and I will give you a bookstore code. I'm the bookstore for this class. And then you're going to have to affirm that you're 13 or older and all other stuff. Once you click on that, you will have access to our activities. Going to our activities, our class. Going to our activities, you have week one measurements. I'm going to have to blur that out after the fact because I think we were able to see some people's grades. Wasn't anticipating that. But we have here our first activity, and the way the activities are set up in Pivot are actually pretty nice, I think. What I've done for you is given you a nice introduction section, including a link to a textbook I often use for students. This is OpenStax. This one's a little bit more advanced, but it goes through a lot of the information, more information than you'll need to know. But it talks a lot about, in this case, physical quantities and units. Gives you some background, including like taking measurements and understanding significant figures and the rules behind significant figures. I got a brief lecture on that a little bit later that we'll talk about, so I'm just going to skim over this. And then you get to the actual laboratory part. Now, since we're online, I can't really give you lab equipment to work with, so the next best thing I think is video exercises. And in these video exercises that you have, you can change around what substance you're looking at. So if you look at this Substance 4, you have this quite large block. I think the lab has you looking at a different substance for part of it, substance 5, which is a thinner block. And then for each of these, you can take different measurements. Up in the top right. There's a little tool button. And then for the tools in this activity, you have a couple of different rulers, a horizontal ruler and a vertical ruler. They give you the actual measurements of these objects. So no, you are not necessarily taking actual physical measurements, but the video allows you to take measurements off of those videos that are accurate to what the video is. So if you're performing this lab in, the real physical space, it would be the exact same as what they're doing on the video. So it just kind of guides you through. And then after the videos, it asks you about measurements. So for this first part, it says, okay, pick object, what is it, 5, I think, substance 3 for this first part. So you're going to go substance 3, load, and then you're going to press play. And once you press play, you'll eventually get a measurement on the balance here that tells you what the mass of this object is. And then you just select like, hey, I think it's 44 grams. And once you submit answer, it'll tell you yes, right, or wrong. No, too much rounding in this case. And then you go on, and there will be interspersed moments of like, this is information you need to know, such as the SI unit system. And asks you, hey, let's do a unit conversion. And it goes on to say, let's change out, or let's use a measuring tool in this case. Pulls up the rulers and asks you to take measurements of the rulers, calculate a volume. So you go through and you just answer the questions. Now, this first assignment is relatively short, I'll say. And it's short because there's a lot of setup to this class that you're going to have to go through. A lot of the time that you're going to spend is getting familiar with the course. Your next assignment is going to be a little bit longer, so just be prepared. They're not all going to be this quick, this easy. However, your labs are going to be graded out of 10 points. 10 of them are based on the questions that you answer here. So, in this case, if you answer the wrong answer too many times, you won't get credit. You'll get 0 out of 1 point there. And you'll see that there are 10 points awarded throughout these multiple choice questions. There's another part of this lab, and this comes into the reflection portion, because after you do the lab, it's always important to reflect upon what it is that we did. And in this case, I'm asking you to go to the week 1 activity discussion post in Canvas. So if you go over to Canvas, go over to discussions. There's also a link in that assignment. There's also a link in module, so there's several ways to get here. Go to the discussion post, and you have a place to put in your answer to your discussion. It also reprompts you for what I'm looking for here. And you can see some of your classmates have already answered, so off to a great start. Now, this first week, again, you are going to post your response and see other people's responses, see what they said. You don't have to reply this week, but in future weeks, there's going to be an expectation of you replying to other people's posts. I want to make sure that there is some student-to-student communication here. And then after you post, maybe a couple of days later, I'll respond to you. So be aware that this is part of the activity, and this will count for 2 of the 12 points of your overall lab assignment. Again, the other 10 coming from these multiple choice questions based on the laboratory exercises. So that's Pivot, and it might take a little bit of getting used to. If you're not like super computer tech savvy, it might take you a little bit of time getting used to getting comfortable with this, taking measurements online. And this is a new thing that I'm trying out to see if it helps students, because previous to this, we were doing a lot of like online simulations, and I don't think it was working out. I don't think students were enjoying it. I think this is going to be a lot more enjoyable of a lab experience for you guys. As you go through this, though, I do want you to give me feedback. I want you to tell me, hey, I'm liking Pivot. This is cool. This is fun. Or, hey, I hate Pivot. This is hard and confusing. Like, I want to make sure that you guys give me feedback as it comes to mind, because it'll change sort of how I'm going to run this class. I want to run this in a way that is convenient and as streamlined for you guys as possible, but I need your feedback to do that. So don't hesitate to give me feedback, especially on this Pivot interactivity stuff. So that's pivot. That's the idea. I want to run through real quick a brief lecture to introduce the ideas that we're talking about this week. Um, and I have to apologize because my writing pad seems to not be behaving today. So I'm going to be writing with a mouse. Hopefully it goes well. And if there's something that's hard to read, you can always, ask me, hey, professor, at minute 15, what were you writing here? I'm not offended if you can't read my handwriting with the mouse. Okay, so I'm gonna change my share screen over to here. All right, and hopefully what we're all looking at is a screen that says sig figs and measurements. That's the content that we're covering this week. Why? Because, well, we haven't really had much time to cover any physics. And I think that it's important to think about, what is the essence of a physics lab and what is the essence of an experiment. And honestly, it all comes down to measurements, being able to take good measurements. It's a huge part of working in a lab, working in a lab environment. Um, so we're going to talk a little bit about, what makes a measurement. And for any measurement, there are two parts that are associated with it, right? Every measurement needs two things. Every measurement needs a number, and every measurement needs a unit. These are the two necessary things to make sure that your measurement has meaning to, right? Because if I say, for example, I am driving my car at 30, no unit attached to it, just saying I'm driving my car at 30. Well, what does that mean? Does that mean that like I'm driving my car at 30 miles per hour, 30 kilometers per hour? Or am I driving my car at a time of 30, whatever that means? You don't really know. You need a unit associated with it to make sure that it has meaning to it. And likewise, to say, I'm feet tall. Like, what does that mean? I'm feet tall. If there's no number there, I don't know how tall you are. So you need both a number and a unit to be able to tell sort of some important information into what the measurement is. And we can take measurements of a whole bunch of different things. You can say, like, class is 1 hour long. Well, what is this? This is a measurement of time. We are measuring time, the time specifically for one class to occur. What is that time? Well, it has a unit and a number. It has one is the unit, or one is the number, right? One is the number associated with measurement, and hour is the unit, right? Class is 1 hour long. You have that number and that unit to tell you exactly how long it is. This is much different than a number associated with a different unit, right? If we say class is one, same number, class is 1 minute long, well, that's a lot different than 1 hour long, which is a lot different than 1 day or 1 year, right? The unit matters a great deal. We always want to make sure to include our units when we deal with our measurements. Always include a unit. If you don't have a unit, it's wrong. That's one of the most common places where students make mistakes, right? We look at another one. I drove 25 miles to work. I drove 25 miles to work. We have a number 25, right? That is the numerical portion of this. It tells you how many of these miles did you drive, and mile is the unit, right? And again, 25 miles is a lot different than 25 feet. I cannot emphasize enough that the unit matters a great deal, right? And then we go on and say, like, I weigh 210 pounds. We have a number and a unit. You cannot forget either of those parts for a measurement to have meaning. You must always have a number and a unit associated with it. We don't want to forget these things. So with every measurement, you need to include these two things, but not every measurement is going to have the same units, right? We can take measurements in different units and they can still mean the same thing, right? A student can say that they are 6 feet tall, right? 6 feet tall, we have six, the number, feet, the unit, tall. But there are several ways to represent this. You can say you are a little over 2 meters tall, right? That would be a similar measurement. Or you can say that you are 72 inches tall. That would be the same thing. It has a different number and a different unit, but they are the same measurement, right? Student is this tall. What is their height? Their height is represented by 6 feet or perhaps 72 inches. How do we do those conversions though? How do we go from 6 feet to 72 inches, for example? Well, to do that, we have to understand that units have qualities of sorts, right? We can say, for example, 12 inches is exactly 1 foot, right? This is a defined conversion, right? That we say 12 inches is 1 foot. We can do a little bit of mathematical trickery here, right? I can say, for example, 12 inches divided by 1 foot. If I take both sides of this equation and divide by 1 foot for this example, well, on the right hand side, it'll cancel out. It'll give you 12 inches divided by 1 foot on the left hand side of this. And this is interesting because this gives you a value that is numerically 1. 12 inches over 1 foot is the same thing as 1. And I have to apologize for the inconsistency between using the word foot and feet here. I meant to convert this to being feet, not foots, and you'll see why in a second. But moving forward, what do we do with this? Well, we take that value that is 1, right? 12 inches over 1 foot, that is equivalent to saying 1. And what we can do is we can take our 6 foot measurement or 6 feet measurement and we can multiply it by 1. And when you multiply it by 1, anytime you multiply something by 1, the value isn't changed, right? It doesn't change the meaning of the measurement. We are still talking about how tall the student is. We take the height of a student, we multiply it by 1, it is still the height of the student. In this case, we take the height of the student, 6 feet, and we multiply it by this really interesting way to write 12 inches over 1 feet. Yes, it is still 1. Value-wise, it is still 1. So it still does not change the value, but what it does do is it gives us an interesting mathematical equation. What we can do next is take all of these numerical parts in the units and separate them out. And when we do that, we have 6 times 12 divided by 1. These are all the numerical parts. And then we have the unit parts over here. And in our unit parts, we have feet on top, we have feet on the bottom. Those will cancel out. And what we're left with is 6 times 12 divided by 1. That gives you 72. And then the feet cancel out, giving you inches. So we do our unit conversion by taking our numerical portion and uh, our unit portion and just combining them together to give us 72 inches. All right, so this is our basics of unit conversions. And the units that we're looking at here, feet and inches, they're part of what we call the imperial unit system. The imperial unit system is the one that we're most familiar with here in the US, but it's not the most common unit system. The most common unit system in the world is the SI unit system. Now, this unit system is a set of units that we use in science to sort of universalize what we're looking at. And there's very convenient unit conversions, right? 12 inches is 1 foot, 12 to 1. There's some weird numbers. And there are reasons why 12 is used. It's not just an arbitrary pick of 12. It has to do with the divisibility of the number. It's not super important here. But you have this measuring system in the imperial units, feet, inches, pounds, all of them. Those are a little bit harder to convert between. The SI unit systems are made to be more easily converted. Now, the SI unit system has our seconds, grams, and meters being the sort of ideas that we're going to be mostly focused on in this class. But we also have other units for like volume, cubic meter, right? Meter cubed, or a liter is sometimes used for our SI unit. We have Newton, joule, watt. These are all units to describe different types of measurements like force, energy, and power. Some of these we're probably familiar with, other of them we're probably not, and you'll become more familiar with them as you go throughout the semester. But these are our base unit systems. Now, this unit system came about during the French Revolution. We created this unit system because we wanted a way to more systematically be able to do science, and the overturning of the French government marked a really distinct time for people to be turning away from these sort of traditional ideas of including units to more like science-focused ideas. Now, what's interesting, this unit of gram, most often we consider the base SI unit to be not the gram, rather the kilogram. We say that the base SI unit for mass is usually the kilogram, not the gram. Sometimes you'll see it as a gram. It's in the case of this chart, but I put it here as a gram for, symbolic sort of reasons. But the base SI unit is usually taken to be the kilogram. And what you'll notice is that they both have that word gram in it, right? Kilogram, even representing it with the same symbol G. But we put this K out front, this kilo. Why do we do that? Well, we do that because we can leverage this SI system with what we call the SI system prefix measurements, where we can take measurements and look at like larger measurements by attaching a unit prefix to the unit itself. So for example, if we look at kilo, like our kilogram, well, what that K actually means is 1,000. K means 1,000. So if you see something that says it's 5 kilogram, well, 5 kilogram, what that actually means is that kilo is standing in for 1,000. So what we have here is 5,000 grams, 5,000 grams. Kilo means 1,000 in this case. And then you have other ones like mega, which means million, and giga, which means billion, and tera, which means trillion, right? So you have these different SI units, prefixes for our different measurements. And you can attach these to any of these SI units to get meaningful results. For example, you can talk about a milli-m second. What does that mean? Well, milli is represented as what? Well, that's a million. So it's a millionth of a second. Or centi, which is 100th. You can talk about a centimeter, cm. And what that means is a hundredth of a meter, hundredth of a meter. And we leverage these prefixes and these base units to create a very diverse measuring system where we can measure things that are very, very small. We can measure a small amount of time, like a femtosecond. That's a very tiny amount of time. Or we can measure something very large. We can talk about like data stored on a computer and terabytes, trillion bytes. So we have a system that now allows us to measure our quantities in different sizes, right? And then we ask the question, what use is this? And specifically, I want to ask the question of like this kilogram stuff, because I said earlier that we often say that the base SI unit of mass is a kilogram. Well, why might that be? Why do we use the kilogram instead of a gram? Well, it's because most things are larger than a gram. Most things are on that order of kilogram. So it's helpful to measure things on the order of what that thing is, right? So we use the kilogram. And, going back to talking about the French Revolution, we made the decision, let's use kilogram. And why did we do that? Well, because again, measurements were often made by trade back in the French Revolution times, and kilogram was a more convenient unit to use when dealing with trade. So, there's a lot of reasons why one might use the kilogram, and it just all boils down to, well, things are not often as small as a few grams. So this is our SI unit system. You might ask, how do you do some conversions? Well, they're not that hard, right? Because now we're looking at factors of 10. All of these are factors of 10, 10 to some power in this case. You can see the different factors on here. So when we look at a question and say, how many meters is 350 centimeters? Well, what we know is 1 meter is what? 1 meter is, I should have written that. That 0.01 meter is equal to 1 centimeter. That's from this chart right here. And we can rewrite this. We can multiply both sides by 100 and get the 1 meter is 100 centimeters. This is sometimes a little easier to work with. When we look at this, we have now an equality that we can use for one of those unit conversion factors that equals 1. For example, we can say 1 is equal to 1 meter divided by 100 centimeters. This is our unit conversion factor, just like we had earlier with the feet to inches. So how many meters is 350 centimeters? We take that 350 centimeters, we multiply it by 1. When we multiply it by 1, we can see the centimeters canceling it out, leaving us with 350 times 1 divided by 100, giving us numerical value 3.5. And the units, centimeters cancel out meters. So 350 centimeters is 3.5 meters. And then we go on to ask, well, what about kilograms to grams? Perhaps we have a measurement of 5.4 kilograms. How many grams is that? Well, we take our 5.4 kilograms, we multiply it by a unit conversion factor that tells us that 1,000 grams is 1 kilogram. So again, this is just numerically equal to 1. So you take that 5.4 kilograms, you multiply it by 1, you don't change the measurement itself, you just change the way that it looks. And when you change the way that it looks, we now have 5.4 times 1,000 divided by 1, giving you the numerical value of 5,400. Kilograms cancel out, giving you grams. So you have your unit conversion. Now I meant to add in a third one here, a third piece here that asks something of the form of 20 milliseconds equals how many question mark seconds. How would you do that? You take that 20 milliseconds and you convert from milli to base unit of seconds. So what is that going to be? That's 1 second is equal to 0.001 milliseconds. You just do 20 divided by 0.01, the milliseconds cancel out, and you're left with what? 0.02 seconds. 0.02 seconds is 20 milliseconds. So you have these different conversion factors for your SI unit system, and this multiplying and dividing by 100, this is the key part, this chart where it's always, factors of 10, we say factors of 10 to the 18 is 1 with 18 zeros after it. So this factors of 10 thing is why this SI unit conversion is so handy. It's no longer dealing with 132 ounces to gallon or something like that, or 12 inches to a foot, right? These are your base SI units. Now, your SI unit of second, well, time when it gets bigger, we start talking about minutes and hours, and those aren't factors of 10, right? It's 60 seconds is a minute, 60 minutes is an hour. So your SI unit is seconds, yes, but we don't often use kiloseconds or megaseconds or gigaseconds, right? We still do use minutes, hours, days, weeks, years, whatever larger unit of time. So something to be aware of. We don't often talk about gigaseconds. All right, so these are our SI unit conversions. The next thing I wanted to talk about was sig figs, right? Because we talk about measurements a lot, and measurements have some degree of accuracy, and we talk about the accuracy or precision of a measurement with these significant figures. And there are several rules to follow with significant figures. This is all about telling you how many digits are meaningful in a measurement, in a number, right? So you have a number, how many digits are meaningful. And first rule is that all non-zero digits are going to be significant. This is always true. Anytime you have a non-zero number in a measurement, that is a significant number. So when we look at these two examples, 1.234, right? These are all non-zero numbers. And since they're all non-zero numbers, that means they're all significant. We have 4 of these significant digits, these significant figures. Whereas 1.2, these are similar measurements. In fact, these can be measurements of the same object with different precision, right? 1.2 grams or 1.234 grams, again, number with a unit attached to it. These could be measurements of the same object with different devices that have different precision, right? These are basically the same measurement, 1.234 and 1.2. But 1.2 only has 2 significant digits, meaning that it's less precise, right? So the 1.2 grams is the less precise measurement. So we take these two numbers and we say it could be measurements of the same thing, but the top one, 1.234, is much more precise because it has more significant figures. So that's rule one. That's easy. All non-zero numbers are significant. Rule two, captive zeros between non-zero digits, those are significant. So when we look at this first example, we have 1 and we have 2. 1 and 2 are significant digits. These middle zeros are captive or sandwiched by significant digits. And since they are sandwiched between significant digits, well, that means they themselves are significant. So 1,002 kilograms has 4 significant digits because of those captive zeros, those zeros between non-zeros. 3.07, again, 3 and 7, those are significant by the first rule, and the second rule tells us that this 0 is also significant, giving us 3 significant figures for this 3.07 milliliter. Again, units are important. 3.07 milliliters measurement. So we have our first 2 rules. Those tell you all about significant digits as far as which numbers are significant, right? And then we have rule 3. There's 4 rules in total that we're going to look at. Rule 3 tells you that any digit to the left of a 0 is not significant. So the first 2 rules are telling you about digits that are. This third rule is telling you about digits that are not significant. What are the non-significant digits? We often call these leading zeros, or zeros to the left of the first non-zero digit. In this case, we look at 0.001 degree Celsius. When we look at this, we can see that these first 3 zeros are to the left of the first non-zero number being 1. That means these first 3 digits, these first 3 zeros are non-significant. Only the 1 degree here is significant. So we have 1 significant. And then what is the unit here? Unit is degrees Celsius. Again, units are important. Cannot stress that enough. Cannot stress how important units are. We look at the next one, right? 0.012. We have 1, 2 being significant by rule 1, right? Rule 1 tells you non-zeros are significant. And then this first one, well, that's the first non-zero digit. So everything to the left of it, all the zeros leading it, are non-significant. So what does this have? This has 2 significant figures because it has 2 leading zeros. So only the 1 and 2 are significant. Okay. Well, that tells us about leading zeros. We heard about captive zeros or central zeros. What about zeros that are trailing? And rule 4 deals with trailing digits. And we say that zeros that are to the right of a decimal point in a number are significant. So in this case, we look at this 0.023. The first 2 zeros are leading zeros. So by rule 3, they are out. They are not significant. Only the 2 and 3 are, right? So we've already eliminated these 2 because they are leading. So this 0.023 has 2 significant figures. Yes, this 0 right there, to the right of the decimal, it is to the right of the decimal. But we've already, by rule 3, expelled it as being non-significant by rule 3. So we know it's not significant, so rule 4 does not apply. There's a hierarchy. Right? If we look at the next one, leading 0, not significant. 2, significant by rule 1. And then we have 2 zeros that are to the right of a decimal, but to the left of the first non-zero digit. So 0.200 has 3 significant figures. Again, rule 4 applies to these because they are non-leading. Now this opens up interesting questions. Some questions might be a number such as 130 centimeters. Why not look at this? 130 centimeters. Well, now this is interesting because we have 2 non-zero numbers. So those 2 are definitely significant, the 1 and the 3. But what about this 0? The 0 is to the left of the decimal point. So rule 4 doesn't apply. Rule 3 doesn't apply because it's not a leading zero, right? And it's not a captive zero, so rule 2 doesn't apply. So what about this zero right here? And the answer is that, well, it kind of depends. It might be significant, it might not. In general, you will be given an indication of its significance. So if it's written like 1, 3, 0, and a decimal point right there, centimeters, well, that decimal point tells you that that zero is significant. This is general notation. It's not always held to be 100% all the time, which is why it's not its own separate rule. But that's a way to indicate that that zero is a significant digit, meaning that this has 3 significant digits. If that decimal point isn't there, well, then it might be, it might not be. It's not super clear. I'll do my best in this class to tell you, like, okay, take this to be 3 significant digits or 2 significant digits when there's that questionable zero there. That zero for which we don't necessarily have a rule, but there might be importance to it anyway. So these are our significant digit rules, and these work for most numbers. And I'll let you in on a little secret in this lab. They're not going to be the most important thing. I think most of the work that we do won't be necessarily surrounding these significant digits. I'll generally tell you if I want it in specific significant digits. However, in your lecture, you'll find that these are more important. It is more important to get a lecture in class. So I wanted to make sure to cover them here. Moving forward, these are telling us about our different measurements, right? But not all measurements follow significant digits. In fact, there are some times when we consider things to be exact numbers. Exact numbers are known to be exact because they have 100% certainty in them. This applies a lot to like integers, right? So when we talk about integers, we might say that there's exactly 12 inches, 12 integer inches in a single foot. That's exact, right? That unit conversion is exact. So we take it to be essentially an infinite number of significant digits. This is important when we talk about calculations, right? We'll get to that in a second. But we have this idea that integers are perfect numbers. For example, like if I look at my roster right now, there are 23 students that are enrolled in this class. 23 students, well, I know that number exactly to the dot, right? So it's known to be an exact number. There's not 22 and a half students or 23 and a half students, exactly 23 students. This is an exact number. And things that follow exact numbers, well, those are going to be integers like counts of students, how many students, counts of anything are integer values. Other exact numbers are conversion factors, so your 12 inches to foot, or 4 quarts to gallon, or whatever unit conversion you have. Those are known to be exact. They are not limiting your calculations. Other things that are considered to be exact are like physical constants, gravitational constant. You'll hear about soon enough in class. The gravitational constant is an exact number. It does not limit the number of significant figures that result from a calculation. Which enters the question of, well, what do I mean when I say resultant calculation? I alluded to it earlier, right? And it's because significant digits are important when it comes to calculations. And when it comes to calculations, it tells us how to round our final result. So there are 2 main operations that you'll probably find, right? There's addition and subtraction, and there's multiplication and division, right? These are your main types of mathematical operations that occur. And both of these have different rules. So for example, with addition and subtraction, the rule is that you round it to the least common digit that is furthest to the right, right? And I'll show you how to do this in a second. So in the example, I give 100 plus 23.46. And then we ask, how many significant digits is the result? Well, we have 100, and we take all 3 of these digits to be significant. See what I did here? I said the decimal point here indicates that these 2 trailing zeros are significant. You say 100 plus, lost my mouse, 100 plus 23.643, right? These are the digits, and the second one has 5 significant digits. So 5 significant digits, 2 significant digits. When you add these directly, you know that you would get 123.64. You plug it into your calculator and it will tell you exactly this value. And that's great. That tells you what the value is mathematically. But the problem here is that significant digits tell you about precision, right? And our value of 100, whatever this measurement was, whatever it came from, this value of 100 is a lot less precise than the value that has 5 significant digits of 23.643. So by assuming all of these digits to be significant, well, that's assuming that you have a lot more precision than you really have. We're kind of limited by that 100. So we say, no, we need to round this to more appropriately tell us how many digits are significant. So how do we do that? Well, with addition and subtraction, we'll take that 100. And what we'll do is we'll add to it the 23.463. And when we take these two values and add them together, we're going to look at the digit that is the last common digit, right? And what is the last common digit? That's right here. The last common significant digits, I should say. That is right there. So that means we will round to this point. So we find the answer, 123.463 here. And we round to this last common digit. We round that 3. And we end up with 123 as being our result. And that's what gives it, oh, what happened here? Why is it 124? Oh, sorry, it seems as though I swapped this 6 and the 4, right? So it would have been 123.643, and that 6 would have rounded up the 3. So it's not 123, it's 124. My apologies for swapping that number, but the 6 rounds up that last digit. So you just round to that least common digit whenever you are doing addition and subtraction. Okay, well, that's wonderful. What about when we get on to the other operation, right? Multiplication and division. Well, multiplication and division, it's actually sometimes thought of as being a little bit easier because the result is going to be rounded to the least number of significant figures in any of the components of your operation. So here we have the operation of taking, Here we have the operation where we are going to take the value 3.0 and multiply it by 12.60, right? You take those numbers, you multiply them together, you get 37.8, and then we can insert some zeros after the fact, however many we want to go down. But not all of those zeros are going to be significant. In fact, we don't know how many number of these digits are significant. We don't know. So what we're going to do is we're going to look at our two measurements that we took, right? Whatever this 3.0 measurement, 12.60 measurement, right? These came from some place. Where did they come from? I don't know. But they tell us something about the precision of their source, right? And that 3.0 came from a source that only gave 2 significant figures of precision, right? The 3 and the 0 are both significant. And that 12.60, that came from some source where it gave 4 significant figures of precision. So when we look at these two, we look at the least precise measurement, the least precise measurement being the one that has fewer sig figs. So this is 2 significant figures. That's less than the 4 significant figures. And that's what we round our result to. We always round to the least significant digits. So we take this 3.78 and we round it to 2 significant digits, right? So we say it's going to be, let's knock off the zeros, 37.8, right? And we look at that and we say, well, no, that is 1, 2, 3 significant digits. We have to round it even further. What do we round it to? Well, we round it to 38. That gives us a result of 2 significant figures, and that's what I found earlier. So we get 38 for our final result. This gives us our result for our significant digits. So working a little bit with examples, let's take 2 numbers. We say 256.2. We add to that 23.655. what is that going to result in? Well, let's go ahead and work out the math. Up in the top right, I'm going to do 456.2. We are going to add to that, again, I apologize for my poor handwriting with a mouse, 655. When we do this operation, well, adding right to left, 5, 5, 6 and 2 give us 8, 6 and 3 give us 9, 7 and 4. So you add those two together and you get 479.855. But again, not all of those digits are significant. With addition and subtraction, we are going to look for that least common digit. In that case, that's the tenths place. And that's where we're going to round. So what is this going to be? This is going to be 479. And then we round off that last digit. The 5 rounds the 8 to a 9. So 479.9 is the correct result. Yes, your calculator gives you more digits than that, but this is the precision that we can apply here. We go a little bit further and we say, okay, well, what if we add some zeros onto there, right? What if we add a couple of zeros? Well, in this case, the least common digit is this thousandth place, right? So in this second case, yeah, it's 479.855 because our individual inputs are more well known, right? Our inputs to the addition are more precise. We know the values, okay? Well, what else do we have? Perhaps we do something like 35.0 times 6. This is multiplication, right? 35 times 6. Well, what is 35 times 6? You take a calculator, you put it in, and when you do so, you get 210, right? 210, but in a multiplication, you want to round to the least number of significant figures. 35.0, that has 3 significant digits. 6.0, that only has 2. So we round this to 2 significant digits. So 210, it's already rounded there, 210. But what we know in our head is that the 2 and the 1 are significant here, and that zero is insignificant. Only the 2 and the 1 are significant. Let's do a little bit different. Let's do 35.0 times 6.00. We plug it into our calculator. Our calculator will tell us the same thing, 210. But this time, because both of our inputs have 3 significant figures, our output also has 3 significant figures. So what we might do here is do 210 with a decimal point afterwards. And that decimal point afterwards indicates that that is 3 significant figures. Remember, we typically say 210 is not representing the same thing as 210 with a decimal point. That decimal point tells us that the second 210, the 210 with the decimal point, is more precisely known. It's more well known. So it's something to keep in mind. All right. So that's the end of the slideshow. That's the end of the information I wanted to go through, and that tells you all the stuff in this opening bit about significant figures. Now, there's a little bit in here about density, and I want you to read through and calculate out density, but it is a pretty quick calculation. And as you go on through it, there are going to be questions that are asking you to round to certain significant digits, right? Because like the difference between 7.05 and 7.1 is probably a rounding thing. So just be aware that significant figures, they matter a little bit throughout the course of this exercise. All right, I'm going to stick around for a little bit longer, answer any sort of questions for people that might pop by. But this recording will be made available. I'm going to post it on YouTube and send out a link to everybody probably a little bit later this afternoon. If you have any questions, as always, feel free to ask. I encourage you again to use your discussion posts. So going to your discussions, I encourage you to put questions into this FAQ discussion post, which is currently a little bit empty, a little bit. I'm hoping that it gets filled up as we go throughout the semester. All right. I think that's all I wanted to talk about. So I'm going to go ahead and end this recording. And I hope you guys have a wonderful day. And I hope I see a few more people in the participants next time.